Okay. So I have to admit I have a hidden agenda here, which is I want to promote by example the idea that knowledge sharing doesn't have to be work related. That if you have something to share that's just like some random fun stuff that you've been doing, then please do sign yourself up on the queue, which has been somewhat empty lately. Now what I want to do today is it's not working. Low bubbles. Okay. Now I don't know how you can see that well because they tend to fall down. So I have a trick here to make them somewhat more stable, which is I actually make just half a bubble on a sheet of glass. And you can see that it's very round. Okay, and this is one of the things that I want to talk about today, which is the history of how we know that bubbles are round and why they're round. So there's a bit of math. I don't know what appetite you guys have for math, so I'm going to keep it like fairly sketchy. And then if you want to know more details, then please do ask. I'm happy to fill in details. Okay, but the first thing I want to talk about is why bubbles are round. But before I get into that, I also want to tell you that it's not quite true. They're not always round. Let's see if I can make an example for you. There you go. So here's an example of a bubble which is not round. In fact, you see I have two bubbles and they meet at an angle there. Whoop, not anymore. And in fact, it looked, okay, let me try again. I'll do a better example this time. I don't know how well you can see this, but they're round. And in between, the first one that I blew might have looked like it was flat in between. But in fact, it's not quite flat in between. It's also round in between. It bulges very slightly into the bigger bubble. Can you see that? I practiced this. Yeah. All right. So so bubbles are round, except when they touch each other and then they meet at an angle. But there's some very interesting stuff actually that happens when they meet at an angle. And in order to show you this more clearly, I'm going to try and make it two-dimensional. So let's try. I haven't seen if this works with the camera yet. So here we go. How's that? I've got two sheets of acrylic here with bubbles in between. So it basically forces the bubbles to be more or less two-dimensional. Okay. And what you see here again is they're round. They have round boundaries. Okay, but they meet at various points at angles. And these other boundaries are, well, this one may or may not be flat, but in general, they're sort of slightly rounded. Okay. Now, one thing that you may have already noticed is that they only ever meet in threes, right? Like at this point, this bubble and this bubble meet the outside, right? At this point, this bubble and this bubble and this bubble all meet, right? Here, I've got these three bubbles meeting. Here, I've got these three bubbles meeting. There is no single point in this picture where there are four bubbles that meet. Now, this is a bit tricky. I'm going to try and force four bubbles to meet, and you have to pay attention because it sometimes happens fairly quickly. But let's see. It's not going to work. I almost managed to get four meeting at this point, but they didn't quite do it. Oh, did you see what happened there? There were four that met. Oh, well, okay, let me try again. Right here, for just a brief instant, there were four that met, and then they all of a sudden split apart into two meetings of three. And this is what happens in general, actually, that you really can't get four bubbles to meet. And if you do manage to get them to meet for an instant, sorry, I'm waving my hands, but you can't see it, right? Because my hands are up here. Anyway, if you do manage to get them to meet for an instant, then they really prefer to separate into multiple meetings of three. Okay? So that's something that was observed in the 19th century. And it's actually not quite true. Well, it's true in 2 dimensions, but it's not true in 3 dimensions, because you see what I can do is I can take No. So here, up here, where's my pointer there? Here I have a point with 3 bubbles meeting, right? And now we failed in 2 dimensions to get a 4th bubble to meet there too, but in 3 dimensions I have an extra trick, which is I can put it on top. There we go. And now, if I can get the camera to focus correctly, you'll see, so I had this bubble. Come on, focus, please. This bubble, and this bubble on top all meet at a point in the middle, right? So in 3 dimensions, you can get 4 bubbles to meet at a point. In 2 dimensions, you can get 3 bubbles to meet at a point, okay, but not more than that. And if you like to do sort of math in higher dimensions, you might guess that if you go up 1 more dimension, you can get 1 more bubble, and you go up 1 more dimension, you can get 1 more bubble, and that's probably true, but I think it's still open, actually. So, okay, so that's basically what I want to talk about today. Why are bubbles round, and why can't you make them touch each other more than 3 at a time? Okay, so let me start maybe with a bit of history, because this is something that people have known about for a very long time. And with any luck, the screen sharing will work. Okay, so the history starts. Okay, the history starts maybe 2,000 years or so ago, more than 2,000 years ago, with this legend that's called Dito's problem. So the story was you had this Queen Dido of Carthage, but she wasn't Queen Dido of Carthage yet. She was just Dido, right? Sailing around on a boat, landed in Africa, and so she had a bunch of followers, and she had an ox hide, and she negotiated with a local chieftain that for some amount of silver, she would buy from the local chieftain however much land she could fit in the ox hide. Okay, and the local chieftain thought that was a great idea. How much land can you fit in an ox hide? And so he agreed. And then what she did is she took the ox hide. So here we have the coast of Africa. She took her ox hide, she cut it into a very thin strip, and she laid it out along the coast in a circle. Okay, so this was the land that she enclosed in her ox hide. It was rather bigger than what the chieftain had bargained for. Okay, but whatever, he had to agree, right? Because I don't know, that's how it worked back then. Okay, and that was the founding of the city of Carthage, or at least the legend of the founding of the city of Carthage. Okay, but the obvious question is, how did she know that she should lay out her ox hide in a circle, right? Why not lay it out in a square, or as a triangle, or as some other thing, right? And the answer to this question is because the circle is the most efficient way to use the ox hide, in the sense that there is no better way. So she has a constraint, right? Which is she has a certain length of ox hide, and she wants to get as much land as possible for her country, right? And so the best thing to do is to do whatever shape maximizes the enclosed area, given the constraint that you only have a certain amount of thing to enclose it with. Okay, and so this is the same thing that happens with bubbles. So it's a fact. Circles maximize enclosed area. For a given perimeter. Okay, so already 2,000 years ago, we knew somehow that this was true, but it was quite a while until we sort of really understood what was going on. And this is exactly the same phenomenon that you see with soap bubbles, because what happens with soap bubbles, well, it's 1 dimension higher, right? It's in 3 dimensions, not 2, but you have a soap film, right? And the soap film has surface tension, and the surface tension makes the soap film want to shrink. Okay, so it makes the area want to shrink, but it can't shrink down to nothing because you have air in the middle, and the air has pressure, right? So the air is putting out pressure to keep the volume from shrinking, and the surface wants to shrink. Okay, and the fact in 3 dimensions is that if you want to have a given amount of boundary for a maximal amount of volume, then you should take a sphere. And this is why soap bubbles are round. Right? So the reason that soap bubbles are round is the same reason that that Queen Dido wanted to make a circle with her oxide, which is that it's the most efficient way to enclose volume. Okay, so okay, so this thing has been studied for a long time. There's a very nice survey article, if you're mathematically inclined, that I'll put in the chat afterwards. But so the basic summary is that the Greeks knew they didn't know how to prove this fact, but they were able to do something that was, pretty interesting. I think that circles are better than polygons. Better. And what I mean by that is, okay, so you have a certain amount of string to make a shape, right? You could start by making a triangle, or you could use that same amount of string to make a square, or you could use that same amount of string to make a pentagon. And what the Greeks knew, it's not too difficult to prove, is that as you add more sides, it gets better and better. You enclose more and more volume, okay? And then in the end, it sort of converges to a circle, and so that's maybe why a circle is the best, okay? But at least to sort of like the tastes of modern mathematicians, this is not really complete, because, how do you know that the answer is not something which is non-polygonal, right? Maybe there's some other weird shape that's not a polygon, which is better than a circle. Okay. And so that brings us to the 19th century, in particular, a German guy named Steiner, Jakob Steiner, who came up with a clever argument, in fact, like 5 clever arguments to explain why other shapes could not beat circles. Okay, and I just want to show you maybe a sketch of one. So the idea is you take any shape, and if it's not a circle, then improve it. Okay. And okay, so he had a bunch of different ways to improve it. I'm just going to show you one, which is, so let's say I have a shape. I want to make a shape where it will be relatively easy to draw the improvement. So maybe this shape. Okay. And then you can rotate your shape however you want. It's not going to change the surface area. It's not going to change the area. It's not going to change the perimeter. So it doesn't really matter which way is up. But okay, I've decided this way is up. And then what I'm going to do is I'm going to take a horizontal line through the middle of the shape. And I'm going to do what's called symmetrization. Symmetrize. Which means that, so basically I'm going to divide my shape into tiny strips. And some of these strips are more to the bottom, and some of them are more to the top, right? And all I'm going to do is I'm going to take each of those strips, and I'm going to shift it until it's in the middle, right? So this strip down here will move up. Let me draw the symmetrized one here. But it's going to be of the same length, right? So this strip here moves up. This point here moves up. This strip moves up. This strip moves up. Well, I've drawn it so that they all move up, but that's fine. And then the final shape after symmetrizing is going to look something like this light blue one I've drawn, right? And the point is that the way I get, so again, the way I get from the dark blue one to the light blue one is I just take every vertical strip and I center it, right? Okay. And well, hopefully it's just clear from the description that the area didn't change, right? Because all I did is I cut my thing up into strips, right? That didn't change the area. And then I moved each strip without stretching it in any way. And so that doesn't change the area. And so after I'm done with the symmetrization, my area has stayed the same. Okay, and what Steiner showed, and I'll probably just skip maybe I'll give a hint as to why it's true, that this decreases or doesn't, well, I say decreases, it might not change it, but it at least doesn't increase it, the perimeter. And it's not actually difficult to see why it decreases the perimeter. And really what it boils down to is it's enough to just consider one strip, really, and do a little bit of geometry, right? So I'll draw the picture and I'll skip the geometry, right? So if you have one strip like this and you symmetrize it, then basically what happens is the two sides become sort of symmetric with respect to each other, right? Like this, like vertically symmetric, right? This length is the same as this length, and this length is the same as this length. Okay, and all you have to do to convince yourself that the perimeter has decreased is just to calculate the perimeter on the left-hand side, which is these two, the lengths of those two red lines, and compare it to the perimeter on the right-hand side, which is the lengths of those two blue lines. And you can see with a bit of calculation that that it's all, the perimeter is always the least when it's symmetric. Okay, so this is Steiner's argument for showing that you can always improve a shape. Now, what happens if you started with a circle? Well, if you started with a circle, there's nothing to do, right? Because if you start with a circle, then no matter which line you draw through it, or no matter which way you rotate it, it's always symmetric. So this operation never does anything. Okay, and on the other hand, it's not too hard to see that if you have something which is not a circle, then you can find a way to do something with this move and therefore improve it. Okay, so this was Steiner's argument, which is sometimes considered to be sort of the first kind of real proof of the whole statement, right? Which is that no matter what shape you draw, the circle. So among all possible shapes that you could draw, the circle is the one that's the most efficient. Okay. But there's sort of an interesting mathematical history story here too, because so this was all happening in the 19th century, which was like a great time of crisis for mathematics, because people had been doing it for thousands of years. And then all of a sudden they sort of realized, wait, hang on, maybe we don't quite understand how logic works anymore and what's true. And they discovered paradoxes. And so they were really worried about mathematical rigor. And Steiner got caught up in this, in the sense that it was a bit controversial. Was it a complete proof or not? And Steiner, I think, thought it was, and many people thought it wasn't. And there was this very clever article by Perron, I think, who wrote it down like this. So he wrote theorem. So I'm going to just sort of paraphrase it. Hopefully you understand what I mean. So a circle is best. Okay, and the proof for every other shape there is a procedure this one that I drew above, this procedure was given by Steiner to improve it. Right. So this was more or less Perron's paraphrase of Steiner's proof. And then, so he wrote this down in a book, and then right next to it, he wrote down the following theorem. So 1 is the largest positive integer. And the proof of this is that for every other integer, or every other positive integer, there is a procedure namely by squaring it to make it bigger. Okay. So the logic of these two arguments is yes.
Just a question about the procedure. So if you apply the procedure to a square, yes, would that change the square?
So you get to choose. So you get to rotate the figure however you like. So if I start with a square like this, and I do the procedure in the horizontal axis like I drew above, it would not change it. But I could decide to draw my square like this, right? And now if I symmetrize, it will change, right? It will change into something like this, more of a hexagonal thing, but not quite symmetric. Yeah, right?
Yeah. Thanks.
And the claim, which, yeah, thanks for bringing this up, because I was, I'm sketching over a lot of details. The claim is that everything which is not a circle, for everything which is not a circle, there is some orientation which makes it change.
Okay, that's cool. Thanks.
Okay. So back to the correctness of Steiner's argument, right? So maybe you see the problem, right? I mean, okay, these two proofs look the same, right? For every other shape, there is a procedure to improve it, so a circle must be best. Okay, for every other positive integer, there is a procedure to make it bigger, so 1 must be the biggest. Okay, but clearly the statement on the right is nonsense, right? 1 is not the biggest, and so something must be wrong with the logic. Okay. Is it clear what the logical mistake is? Anyone want to say?
Yeah, I'm not sure. Okay, go ahead.
Please go, Philip. No, you started.
Well, I was just about to say that there needs to be an argument that the premises implies the conclusion. Like I feel like there's just something missing.
Okay,
and that
but what
is, of course.
What's missing though? Right? So that, I mean, I said it in one sentence instead of going into detail, right? But every other shape besides the circle can be improved.
Yeah, and
right?
that just doesn't imply the theorem. So what's missing is some piece in the chain of reasoning.
Right. Well, so maybe I can just give it verbally, right? So if everything that's not a circle can be improved, then they cannot be optimal, right? Things which are not circles are not optimal, and so then it must by elimination, right? It only leaves a circle to be the best.
Okay, so maybe there is no optimal shape, and you can always make it better.
Exactly, right? So the missing thing here is the existence of an optimizer, let's say, right? On both sides, right? Because this is, of course, also missing in the other theorem, right? On the right-hand side, right, 1 is not the largest positive integer, because we know there is no largest positive integer, right? And so just the fact that we've ruled out everything besides 1 doesn't imply that 1 is it. Okay, so you have to apply the same rigor to this problem with the circles, which is just because we prove that everything else can be improved, right, doesn't imply that the circle is best. Right? It could be that there are like some weird shapes that just get better and better and better, and there's no actual global optimum. Okay, so this was yeah, I mean, so it turns out there is, right? And just sort of, for historical completeness, I think this was shown by Weierstrass in like 1879 or something like that. Okay, showed there is an optimizer. Right. And that finishes the story, right? Once you know there is an optimizer, then this argument by Steiner completes the thing, right? Because the optimizer could not be anything but a circle, and so a circle must be best. Okay, and so since then, things have gone, and then okay, so this was for 2 dimensions, and I think that Schwartz in the 1880s somewhere did 3D. Okay, and also probably higher dimensions, right? So now we know really that circles and spheres and so on are the most efficient way to enclose areas. Okay, so that's why circles are round, right? Sorry, that's why soap bubbles are round, right? Soap bubbles are round because the physics makes them want to contract the boundary while maintaining the area, and a round shape is the most efficient way to do that. Okay, so just want to yes, Jan.
Yeah, what kind of proof is the one of rigor stress? Is it the topological argument, like by compactness or something like that, or is it something more analytical?
It's definitely compactness. I'm not sure I remember exactly the way he did it, but one way you can do it is by doing compactness for you study the problem for polygons, because polygons are compact, right? It's just a finite collection of points, and so then you can do this sort of argument where you say, okay, you take an arbitrary shape. If it's not a circle, you improve it slightly, and then you approximate it by a polygon, which is better than your original, because your improvement is strictly better than your original, and so you can find a polygon that's in between there, and then you apply the compactness argument for polygons, and then you get the final result.
Okay, so you have a sequence of converging polygons, so then this converges to something like that. Okay. Yes,
there is a sort of modern. So this topic was developed quite a lot in the 20th century by sort of analysts like De Giorgi and bunch of Italians, Gacciopoli, and so they have also sort of very sort of analytic ways of doing it, but it boils down to compactness always. Like it's nowadays people talk about compactness of sets of finite perimeter with respect to whatever norms, right? But it's really compactness.
Okay, thank you.
Right. So, okay, I just want to say like maybe two more things, one of which goes back to those like multiple bubbles, right? So we talked about multiple bubbles, and this was, so multiple bubbles were first sort of considered by Plateau in the 1800s, late 1800s. And he learned, he pointed out a number of cool things about multiple bubbles, including the fact that you never want to have 4 meeting at once, right? And basically the reason you have, so what's the mathematical formulation of multiple bubbles? Well, let me just talk about maybe 2 bubbles, right? So with one bubble, right, you want to enclose a volume with the minimal amount of soap film, right? If you have 2 bubbles, it's the same problem, but now you have 2 volumes, right? You want to enclose 2 volumes, right? Volume A and volume B, using the minimum amount of soap film, right? And this soap film in the middle only counts once, right? You only count it, it's on the boundary of A and the boundary of B, but you just count it once because it's only one bit of film, right? And if you have 3 bubbles, then you want to enclose 3 volumes using the minimal amount of total boundary, and so on. And so this is the problem that Plateau considered, and he showed that you should never have them meeting in 4, because if you have them meeting in 4, then you can improve it by having them, but you just sort of perturb this a little bit by stretching that out and modifying these boundaries here until it becomes 2 meetings in 3. And if you do a little bit of geometry, you will see that this is always better. You just do like a local perturbation, you've gone from 4 to 3, and you've improved it. And so what this means physically is if you by some external forces, you make 4 bubbles meet at a point, it actually will never stay there. And it's actually a lot of fun to play with if you have, so what you need to do is you get 2 acrylic plates and you cover them with bubble mix and you blow bubbles, and you can see them like, you try and force them to meet at 4s and they just always flow away. Someday I'm going to try and capture this on video because it's a little bit hard to point out live, but that's what it does. And there's one more cool thing about multiple bubbles, which maybe you noticed from the camera before, but I'm going to show you again in case you didn't. Oh. Okay. Which is that. Not really in the light, is it? Okay. And it's also not really a focus. Not sure how to improve this. Focus on it. No. Okay. I don't know how easy this is to see, but every time, so they only meet in threes, right? They never meet in fours. But not only that, but every time they meet in threes, they meet at 120-degree angles. Oh, maybe it will help actually if I stop sharing this, because then it'll make my other camera bigger. Right? They meet in threes, but not only do they meet in threes, but the angles between every pair is 120 degrees. Okay, this is even true here where the boundaries are quite curved, right? So it looks like when you zoom out, it looks like this is not 120 degrees, right? Because this one sort of goes off like this, and this one sort of goes off like that. But if you actually zoom into the point, right, and taking the, right, really zoom in and ignore the curvature, then you actually, yes, this line, if I extend out the tangent, goes like that. And this line, if I extend out the tangent, goes like that. And they are all 120-degree angles between all of the bubbles. Okay, and that's also something that Plateau showed, which is that if they're not 120 degrees, then there's some sort of local perturbation to make them better, and therefore it always tries to find 120-degree angles whenever three bubbles meet. Okay. Yes.
Yeah, I think I have a bit of a hard time being sure about the argument. So you said something like the surface tries to shrink, mm-hmm. and the pressure tries to. But I think there's a step missing between that and necessarily the surface tries to optimize for the best volume. I don't really see the logical step. I guess there's something that could be said around symmetric causes, having symmetric effect or minimal energy or something like that. But right now, I think I'm missing something here on the physical. Not the physics.
Right. So there are a number of points that I'm glossing over. So I'm not sure if I understood exactly what. So there's the issue of global optimum versus trying to optimize locally, which are two different things. Was that what you were referring to?
Not really. I think I'm missing the step between the physics and therefore bubble tries to optimize their volume over their surface.
Right. Okay. So there's a number of different ways of framing it, which all turn out to be equivalent. Okay. So you can say I want to maximize my volume for a given surface, or you can say I want to minimize my surface for a given volume. Okay. Those are equivalent because there's some sort of homogeneity, right? If I improve my surface while keeping my volume, then I can then scale back out to put my surface back at the original while increasing my volume. Right. So because of the scaling, those are equivalent. Now the physics one is sort of different altogether because air is compressible, and so what's actually being preserved is not the volume but something else. Right. There's a pressure term which tries to equalize. But you can put that in a Lagrange multiplier or something, and it's the same as solving the constraint problem. Like if the answer is always going to be what shape does the bubble find? Right? Whatever shape the bubble finds, it has a certain volume. Right? And at that certain volume, the inside is at a certain pressure. Okay. Right. So now what I do is I consider the circle, I compare it to the sphere with the same volume, and the sphere with the same volume will also have the same pressure. Right. And so sort of optimizing for given pressure is not equivalent to, but the answer is the same as optimizing for a given volume.
Okay.
Does that make sense?
Yeah, I think, but then I get the answer is that you just do the physics and find this problem, this optimization problem.
Yes.
Yes. Yeah.
Yes.
I think this is. I
Um,
mean, is
and there's
there a way to understand it also, even forgetting the problem of the optimizing problem, framing it as, because it's equilibrium, you know, it cannot really, I mean, it has to be symmetric in some sense, or at least locally.
So symmetry is very interesting because actually, like with one bubble, yes, but with multiple bubbles, no, right? Like, so this thing here. Oh, where is it? There. This has no symmetries.
Right.
Um, and there's actually like, so you mentioned equilibrium, which is very important because the optimum will always be in equilibrium. But it's actually a very interesting question. Like, are there equilibria which are not optimal? And for a single bubble, we know that the answer is no. That the bubble is the only equilibrium solution. But once you add more bubbles in, then it's an open question. Whether there are, so you can ask multiple questions. You can say, okay, what about equilibrium solutions? And then you can ask about what about stable equilibrium solutions? Because you can have equilibrium solutions like this plus sign, which are unstable in the sense that you can theoretically put them there, but it really wants to move away. And there are other equilibrium solutions, and as far as we know, they are not stable, but it's not actually known. Yeah. So actually, yeah, I was trying to simplify by going from the physics to the math of just optimizing this thing, but there is like some interesting stuff that I glossed over in doing so. Yeah. Yeah. Even in yeah. Okay. Never mind. I won't say that. That's getting too much into the weeds. I do want to finish with one open question, which I think is like cool because it's a math question that's been open for a while and it's so easy to state. So let me start with a version that's known. Okay, which is I have a glass square, and I blow a bubble inside this glass square, and I want to know what shape does it take. Okay, so okay, I say blow a bubble, but I really mean the optimization problem, right? I want to enclose a region of the square with a given amount of boundary, and I want to maximize the area that I enclose. Okay, and now the reason that this glass square is relevant is because I only pay for the amount of soap film. I don't pay for the glass, right? So if my shape is this shape, I only pay for the red part. I get to enclose this area, but I don't pay here, right? The optimization is only concerned with the amount of oxhide that I'm using, right? And not the length of the coastline. All right. Now, this one is not too hard, but the answer is like a little bit complicated. So you might think the answer is a circle, and it's not. Okay. The answer depends on how big the enclosing volume is, right? So one possibility is that the answer is a quarter circle hugging a corner. Okay. And this is the answer if I'm trying to enclose just a little bit. If I want to enclose more, then the answer changes, and it becomes a straight line enclosing half of the square. Okay, and these are the only two answers. So depending on whether I want a small bit or a big bit, I should have drawn this one bigger, because this one is only the answer when it's sort of largish. Right? Okay, so this is the answer of what are the optimal shapes to enclose a bubble in a square. So now the open question is to do the same thing in 3 dimensions. I have a cube, right? I have a cube and I want to blow a bubble in it. And the conjecture is that there are 3 possibilities. It's a sphere hugging a corner, an eighth of a sphere hugging a corner, or it's a quarter of a cylinder hugging an edge, or it's a flat line, a flat surface. Okay, but this is open. I don't know. It seems very easy. Yes. Okay, so that's all I have about bubbles. I encourage you to get out your soap bubble mix and make them yourself. Any more questions? Stop recording.